So we welcome Mustapha Maamache today, who will talk about time-dependent pseudo-squeezed coherent states. Please go ahead.
Okay, thank you, Andreas. Thank you for organizing. And I would like to specify that the title has been changed because when I sent the abstract, I sent you your abstract. This is not the same title.
That's and okay.
Here we present a definition and the properties of time-dependent pseudo-squeezed coherent state. For this, we introduce what we call the pseudo-squeezed bosonic laders operators obtained as a squeezed transformation of the pseudo-boson annihilation and creation operators. And we obtain the we define the pseudo-squeezed coherent state by applying as an usual coherent state by applying a pseudo-displacement operator on the pseudo-squeezed vacuum. And finally, we end with an example, which is the non-Hermitian Swanson-Hamiltonian. The talk is divided in 3 parts. The first part concerns the recording of a coherent state for Hermitian system and how we construct also a squeezed coherent state for non-Hermitian system. And we go to the time-dependent pseudo-squeezed to the time-dependent non-Hermitian system, and particularly we construct the pseudo-squeezed and the pseudo-bosonic coherent state. And we apply this to Swanson-Hamiltonian. As you know, the coherent state is obtained for the simple harmonic oscillator are firstly a destruction operator in the state. And this coherent state alpha can be obtained by applying a displacement operator, which is this, on the vacuum of the oscillator harmonic. And in 3 ways, this coherent state can also obtain when this state minimizes the uncertainty relation. The coherent state alpha are normalized but not orthogonal. And in quantum physics, we can introduce squeeze operator defined like this, defined in function of the creation and annihilation operators. And the action of this squeezed operator on the ladder operator A and A daga and A daga gives this relation and define also this is a Bogoliubov transformation that we call this Bogoliubov transformation. This gives also a new ladder operator B and B daga. And we can define also a squeezed vacuum from the vacuum of the oscillator harmonic. This squeezed vacuum is defined by applying the squeezed operator on the vacuum of the oscillator harmonic or harmonic oscillator. Because I speak in French and English simultaneously. And here, the squeezed operators produce, we can define a squeezed coherent state by applying on the vacuum of harmonic oscillator a squeezed operator and the displacement operator. And in this case, we obtain that we call this a squeezed coherent state. We can apply first this operator or this operator. And note that these two operators does not commute. And these squeezed coherent states are also in the state of the annihilation operator or destruction operators. This this is the coherent state. It's a recoil of the coherent state for the harmonic oscillator. And when we have an arbitrary dynamical system, we can define a coherent state by using an integral of motion or an invariant, a quantum invariant defined by this relation. This relation specify what the invariant is, the quantum invariant obey to this equation. And when the Hamiltonian H is self-adjoint, we can also define the conjugate of E by this equation. And in this case, we one obtain two independent mutually Hermitian conjugate linear equation of motion, which verify, we impose to this invariant to verify this relation of commutation. And we can define in this case that E dagger are a creation and annihilation operator. And consequently, we can define an end state of E. In this end state, we call this the generalized coherent state, which can obtained also by the displacement operators D defined by this relation. And we use the same strategy as the previous case. We can introduce a squeezed operator defined like this. And this operator is defined by quadratic laders operators. And the Bogoliubov transformation is given by this relation. This is the same relation as the independent case, because here we study a dependent case. And we can also define the vacuum, the squeeze vacuum, when we apply the squeeze operator on the vacuum. The squeeze operator can also act on the coherent state, and we produce, in this case, the squeezed coherent state. This is the squeezed one. We apply first the squeeze operator on the vacuum, and after we apply also the displacement operator, we obtain which we call the squeezed coherent state. And when C equal is equal, this squeezed coherent state becomes an ordinary coherent state. This is for the case of Hermitian cases. But recently, there is a study on the non-Hermitian system. In the non-Hermitian system, you are a specialist of this because the meeting is concerned with the non-Hermitian system. The non-Hermitian system say that the Hermitian conjugate age can be linked to the Hamiltonian age via a linear invertible Hermitian and the positive metric eta. In this case, we can also define a pseudo boson, which are a pseudo Hermitian extension of usual boson and are obtained for the modification of boson commutation relation as follows. And where A and E bar, A is a destruction operator and A bar is a creation operator. And A bar daga and A daga are also creation, annihilation and creation operator, verifying this commutation relation. And there are linked by this relation. This is defined associated to H, and A bar daga is the annihilation operator associated to H daga, to the hermetic conjugate. And the end state of E and E bar daga are what we call the pseudo-coherent state, or the pseudo-bosonic coherent state, which can also, these also are obtained from the action of a displacement operator D and D bar daga on the vacuum psi0 and phi0. The D and the D bar daga are defined by this expression and also are linked by the relation, by this relation. This is the pseudo, this pseudo later has been introduced by Trifonov and also studied by Fabio in a lot of paper. Here we address the problem exactly the time-dependent pseudo-boson and pseudo-coherent state. And we define E and E bar associated to the non-Hermitian Hamiltonian H, and E bar daga and A daga associated to its adjoint H daga via this relation. This is the relation which defines the invariant or the integral of motion. And H and the H and H is govern the big psi H. This is the equation, the Schrödinger equation. And this, as you know, the solution of this equation are obtained by the end state of E multiplied by a phases. This phase is obtained as a mean value of time derivative minus H in this state, in this end state. And in order to construct a pseudo-bosonic coherent state, we consider that the A and E bar, A this is non-annihilation operator, and Ibar is the associated creation operator, associated also to Ash, and Ibar, Daga, and Adaga equal this commutator equal to 1. And these operators are related, are linked to them via this relation. This is the metric. And here, as you see, this is a time-dependent metric. And we can obtain, here we can construct also the pseudo-bosonic coherent state obtained from the vacuum C0 when we apply on this vacuum, we apply the displacement operators, defined via or by the integral of motion, E and E bar. And we obtain also the pseudo-bosonic coherent state associated to the Hamiltonian H plus also. These coherent states are normalized when we take the scalar product between phi alpha and the psi alpha. This product, this and this is also this define the metric products, scalar product, and D associated to H plus and the D associated to H can be linked via this relation. And here we can define also the vacuum, which is described by A and E daga. This is these two concepts are associated to H plus. And we can define the coherent state or the pseudo-coherent state, bosonic coherent state, as the Young state of E with Young value alpha. And here also, this is an Young value alpha, and alpha are independent of time, because these A bar daga and A daga are of motion. This is the coherent. Here we have defined the coherent state, the pseudo-bosonic coherent state. Now we have a background to define the squeezed coherent state. In the squeezed coherent state, we introduce what we call as the squeeze operator, defined by the quadratic A bar and E. And this squeeze operator, when we apply this on the vacuum C0, the vacuum of A, we obtain the vacuum, the squeezed vacuum state. And now, when we apply, we use the Bogoliubov transformation, we obtain these two operators. This is a ladder operator and also R integral of motion, which verify these two equations. And we impose that these two operators are verify this commutation relation. And we can consider this as a creation and annihilation operator. And now when we solve when we apply the B on the squeezed vacuum, we obtain 0. This is the destruction relation between the squeezed vacuum and the ladder operator B. And now we have the possibility to define the squeezed coherent state when we apply the displacement operator, the displacement operator on the vacuum, on the squeezed vacuum. This displacement operator is defined as is similar to the displacement operator of the usual coherent state. Is defined as an exponential of B bar and B with gamma and gamma dagger and gamma conjugate. This is exactly the same strategy to define the squeezed coherent state or the squeezed bosonic coherent state as the coherent, similar to the coherent state. And these coherent states are also an Young state, these squeezed coherent states are also an Young state of B with Young value gamma. And the gamma is a combination, a linear combination of alpha and alpha dagger. And as you see, that the pseudo-coherent state is obtained first by acting with the pseudo-squeeze displacement operator T on the pseudo-vacuum state after we apply the displacement operator D. And this is the definition of the squeezed coherent state. And we can also define the vacuum, the squeezed vacuum associated, this is the squeezed vacuum, associated to the conjugate H, the Hamiltonian IH plus, like this. This is the squeezed vacuum. And when we apply the squeeze of the displacement operators on this pseudo vacuum, we obtain automatically the squeezed coherent state, which are also an Young state of B dagger bar and of A dagger. This is the phi is the squeezed coherent state associated to H dagger, and the C alpha C is the squeezed coherent state associated to H, and this state P and the Psi are over complete set and verify the identity basically. Now we have defined the pseudo-bosonic coherent state, the time-dependent pseudo-bosonic coherent state, and we have also defined the pseudo-bosonic squeezed coherent state. Now we can apply our formalism to Swanson, a famous example, a Swanson Hamiltonian, defined by this expression, and where omega of t, beta of t, and lambda of t are complex parameters, are time-dependent complex parameters. And E and E dagger are the creation and annihilation bosonic operator verifying this. Maybe this also is the ladder operator of harmonic oscillator. And we introduce an integral of motion, a linear integral of motion, a linear combination of E and E dagger, where these parameter delta 1, delta 2, and delta 3 are a real parameter, with delta 1 is different of delta 2. This is a complex integral of motion. And when we introduce this in the equation, in the invariant equation, or of a time derivative of E equal to the commutator of E and H, we obtain this equation of motion. We obtain this is a parametric equation for the parameter delta 1, delta 2, and delta 3. Delta 3 is a constant. We can choose this constant equal to 0, and we obtain this equation. To solve the time-dependent quasi-hermiticity, we make an ansatz for the time-dependent metric, where these parameters are defined like this, and we deduce that eta, this relation between E and E dagger. And we can express the E bar and E in this in this form, and we impose that E and E bar are a creation and destruction operator, verifying the commutation relation equal to 1, we obtain this auxiliary equation. Now, this is a theory, and when we solve these equations, it's better to go to an X representation, or in X representation, and for this case, we can choose E and E dagger like this. We obtain E. This is the annihilation operator of the boson, and E dagger is the associate creation operator. And if G and F tilde and G tilde are obtained by this expression, and verify this equation, and this equation is derived from the commutation relation. And in addition, the operator B and B bar can also be written like this, in this form, where if F Xi and G Xi, F tilde Xi and G tilde Xi are obtained in this form. And in order to construct the pseudo-squeezed coherent state in the position representation, we have to express this vacuum state in the X in the position representation, and to solve this eigenvalue equation. And this eigenvalue, the solution of these two eigenvalue equation are determined by a Gaussian, by a Gaussian function. This is the vacuum, squeezed vacuum associated to B, and this the squeezed vacuum associated to B dagger. And here we can express T, which is displacement operators, in this form. And when we apply this in the squeezed vacuum, this is the displacement of. When we apply this in the squeezed vacuum or in the Gaussian squeezed vacuum, we obtain, this is also the same, we obtain a coherent state in the form of a Gaussian state. This is the coherent state for H, for the Hamiltonian IH, and the Gaussian squeezed state for the Hamiltonian H dagger. And we can verify that the probability, the density probability is also Gaussian at any time. And when we integrate this, when the pseudo time, the pseudo probability density, you can show that this pseudo is conserved, is equal to 1. For this, I thank you, and excuse me for my pronunciation in English pronunciation, because I have really a problem to express my idea in English. Thank you very much.
Thank you very much.
Thank you very much.
Any questions?
Can I ask one?
Go, Fabio.
Mustafa, can you go to Formula 23?
23.
Yes, please.
Yes, this.
Okay. One less. Okay. So I see this exponential, this displacement operator. I have a sort of a mathematical question. Sorry for that. The point is that when you work with ordinary coherent state, D, the operator D is unitary. So it's okay. You can do all the computation that you like. Mm-hmm. But here, your operator, your displacement operator is not unitary anymore.
Yes.
And so I'm wondering how you define, if you are thought about this. I know there are problems in the rigorous definition of this operator. So I'm wondering, maybe your computation are more formal than mathematically correct, rigorous. Sorry.
Yes, you have. I agree with you, but this is not unitary. The unitarity is defined by this relation. Yeah. When I take, this is the relation, the pseudo-unitarity between these two coherent states, and the philosophy of defining this coherent state at in this form, and this in this form, then one can take the scalar product with eta, with the pseudo-unitarity, pseudo-Hermitian operator eta. We have in this case these two, or in other terms, this is the B orthonormalization. This is the B orthonormalization of this case. And for this case, we have exactly, when we use the metric eta, this is equal to 1. This is, and these two operators, yes, are not unitary, but with eta, we can define an unitary operator.
But you need, for instance, eta to be bounded, no? And eta to -1 to be bounded. Otherwise, you get into trouble.
Yes, yes.
Okay. Okay. Thank you.
Thank you.
Any more questions?
I have a question.
Okay.
For yourself?
No, for all people that listen my talk, probably he doesn't understood my talk from my English, my bad English. What am I doing? Okay.
What is your question?
I finished my question.
Oh, okay. Oh, I was still waiting. Sorry.
Yes.
Anyone from the audience to ask a question? If not, I suggest to thank Mustapha again. Yeah, thank you very much.
Thank you. Thank you very much.
Okay.
Okay.
Bye. Bye, everyone.